In this video, I'm going to go over Aldol condensation, microaddition, and Robinson annulation. So we're going to start a review of acid-base reactions, and we are going to start with Aldol condensation, right? So let's say we have this aldehyde right here, and we react it with a strong base like NaOET or ethoxide ion, and the solvent is going to be ethanol, right? So whenever you see Na, that's associated with a positive charge, meaning that whatever is attached to it is going to be negatively charged. So our base here is going to be this ethoxide ion here, and this strong base here is going to look for the most acidic proton, right? And when you have an aldehyde right here, the aldehyde hydrogen is not going to be the acid, right? It's not acidic. It does not want to get deprotonated, right? So we can either have hydrogen A here or hydrogen B here be deprotonated. Now, if you think back to 118A, if you deprotonate, let's say hydrogen B, like this one right here, and give this carbon here a negative charge, we're going to get this conjugate base, where we have a negative charge or carb anion on this carbon right here, right? But if we were to, let's say, deprotonate hydrogen A, or that carbon right here, which is the alpha carbon, because it is one carbon away from the carbonyl carbon, we're going to get this conjugate base right here, where we're going to have a carb anion or a negative charge on the alpha carbon. And let's compare the stability of these two conjugate bases. This conjugate base right here is more stable because it can do resonance with the carbonyl, like that, right? And this right here is what we call an enolate ion. Okay. Whereas if you look at this conjugate base over here, this negative charge here cannot do resonance at all because there's an sp3 roadblock right there. Right, it's too far away from the carbonyl carbon to do resonance. So because of that, this proton here is going to be more acidic than this proton here, right? So we're going to deprotonate that alpha carbon, right, to create this enolate ion. Okay. So let's say the first step here, the strong base, ethoxide ion, grabs that alpha proton and generates the enolate ion. Right, and I'm drawing the resonance form here because this is the major resonance structure. Since the negative charge is on the more electronegative atom, oxygen, right? You can like read it on the carbon, but that's the less major resonance contributor, or the minor resonance contributor, because the negative charge is on the carbon. Okay, now once we have this enolate ion over here, the nucleophile is going to be this alpha carbon here, the star carbon, not the negative charge on the oxygen, right? Because the oxygen here is stable with the negative charge. If you were to compare, let's say, the negative charge on this oxygen versus the negative charge on this carbon right here, the negative charge on this carbon is less stable because carbon is less electronegative than oxygen is. So that means that this carbon here is going to be the nucleophile, right? So you can draw out the next step from this intermediate, or you can draw it from here, right? Which, because we have an aldehyde here, assume excess amount of that, I'm going to bring in a second equivalent of the aldehyde to serve as the electrophile. And the electrophile is going to be this carbonyl carbon here because it is partial positive charge, since it is attached to an electronegative oxygen atom right there. So you could use either intermediate to attack that electrophile. I'm going to use this one right here, where we're going to reform the carbonyl and have this starred carbon attack that dot carbon and push the double bond to the oxygen, right? And that's going to give us this intermediate right here, where the carbonyl is reformed. This is the starred atom. This is going to be the new bond between the star and dot atom. And then this is the dot atom right here, the electrophile that got attacked, right? And this is the new bond that was formed from this arrow right here. And then this dot carbon here is attached to an ethyl group. So let's draw that ethyl group out like this, 1, 2. And I'm going to leave this hydrogen out as invisible. And this double bond oxygen becomes a single bond O minus right there. Okay. So right now we're doing self-Aldol condensation. Okay. Now from here, this O minus here can get protonated by the proton source we have, which in this case it's ethanol. So when it gets protonated, it would be this right here, which this is what we call an aldol, which is aldehyde and the alcohol, right? The alcohol here is specifically beta to the aldehyde, carbonyl carbon, right? This is the carbonyl carbon right here. This is the alpha carbon, and this is the beta carbon. The alcohol is at the beta carbon. But usually we don't stop here. We keep going to do aldol dehydration, right? And usually other professors, they put like heat to make that go through. But for this summer session, I think Levens would assume that it goes all the way down to aldol dehydration if it can, right? And it can because there is at least one alpha hydrogen in between the carbonyl carbon and alcohol, right? So we won't stop here. We're gonna keep going to do aldol dehydration to get this product here. So this alpha proton here is acidic, where we're gonna deprotonate it to reform or generate the enolate ion again, right? Okay, and this might be important. Every single reaction here is reversible in the mechanism up until the last step, which we're going to go over soon, right? So that might be important for vocab or mechanism, but once we generate this enolate ion over here, this is going to be the irreversible step now, where we're going to reform the carbonyl, push this double bond over to create a double bond over there, and then kick out that OH leaving group, right? And this looks weird, right? This looks like it's a bad leaving group, but because we are in basic conditions and we have heat around, this is able to leave. And this is going to be an irreversible step in the mechanism here, right? And this is going to be our final product for this self-Aldol condensation reaction, right? And we could specifically call this an alpha beta unsaturated carbonyl, right? And that's because this is the carbonyl carbon, this is the alpha carbon, and this is the beta carbon. And we see that there is an unsaturation or double bond between the alpha and beta carbon relative to the carbonyl. So that's why we call this an alpha beta unsaturated carbonyl. And this one right here is an aldol because there's like a carbonyl and this is alcohol, beta to the carbonyl. Okay, and that was self-Aldol condensation, right? I'm going to show you guys how to predict the product quickly without doing the whole mechanism. Okay, so we see that this time let's use NaOH and water, right, as a reagent, where NaOH is the base, H2O is the solvent. We have one aldehyde in excess, so we know the nucleophile is going to be the alpha carbon, the electrophile is going to be the carbonyl carbon, but a second equivalent of that, right? So I'm going to draw in the second equivalent of the aldehyde, where this carbonyl carbon is the electrophile or the dot carbon. And here's what I do to predict the product quickly. I first draw out the starred molecule as is, copy and paste, do not change anything, right? And then what I do is I draw out a new bond between the star and dot carbon, right? This right here is the new bond. The dot carbon is attached to an ethyl group, so let's draw that ethyl group out like this, and the dot carbon is going to have an OH like that attached to it, which came from the carbonyl right there, right? But for Levens class, assume that even if you have no heat, you're going to get rid of this OH right here and create a double bond between the star and dot to create this alpha beta unsaturated carbonyl as the final product right there, right? Not all reactants would be able to do that, because let's say, for example, you have this aldehyde right here and you try to do aldol condensation with this base and reactant, right? Let's draw out two equivalents of it. right? To show that the first equivalent here, the alpha carbon is the nucleophile after it gets deprotonated to generate the enol ion. And then this carbonyl-carbon here is the electrophile, right? So let's do that trick, right? Without doing the whole mechanism, copy and paste the nucleophile atom as is, right? Make a new bond between the star and dot, right? Where this right here is the new bond between the star and dot. This dot here is attached to an isopropyl, so let's draw the isopropyl out. And the H is going to be invisible or implied right there. And then this carbonyl or carbon double bond oxygen becomes an OH, right? Now in this case right here, we cannot get rid of that OH and put a double bond between a star and dot, right? Because let's try to do that. Let's erase that OH and put a double bond between the star and dot. There's a big problem here, right? Especially for this carbon and this carbon here, because remember, this carbon still has a hydrogen. They break the octet rule, right? Wait, actually, this problem here, this carbon here does not have the problem. This carbon does not break the octet rule. It has 4 bonds, 1, 2, 3, 4. But this carbon here definitely breaks the octet rule. 1, 2, 3, 4, 5, right? So we cannot get rid of that OH and get to the alpha beta unsaturated carbonyl. We just end at the aldol product right there. Okay, now that's aldol self-aldol condensation on how to predict the product quickly. But now let's think about this in retrosynthesis. So let's say you're given an alpha beta unsaturated carbonyl, and then you want to figure out what reactants created this product right here. Okay, so the first thing you do is you locate the carbonyl, which is this right here, and then you label the alpha and beta carbon. Okay, this alpha carbon here, well, this is going to get into the next thing, so I'm going to give you guys a different problem here. So it would then interfere with that. Okay, so let's say we have this alpha beta unsaturated carbonyl. First thing, you locate the carbonyl, which is this right here, and then you label the alpha and beta carbon, which is there. And then from here, the alpha carbon is going to be the star, right? And then the beta carbon is going to be the dot, right? The star meaning the nucleophile, the dot meaning the electrophile. Then what you do is you cut the bond between the alpha and beta carbon, and then when you go backward here, the starred molecule stays as is. Nothing changes to the starred molecule, right? So this starred molecule here will become like this aldehyde right here when we cut it up, right? We're trying to figure out the reactants here, right? That created this product right here. Okay, now this beta carbon here, or the dot carbon, had an OH before, and that OH came from a carbonyl. So let's draw the carbonyl out, which is attached to the terbutyl, and it has an invisible implied hydrogen. So let's draw that out as well, because this is an aldehyde. And we see here that this right here is going to be the electrophile, and this right here is going to be the nucleophile for this aldol condensation, right? Where the reagent is going to be some strong base like that. And because notice out here, the nucleophile and electrophile are separate molecules, right? They're different molecules. This is going to be a mixed aldol condensation, right? There's 3 types of aldol condensations. The first type we went over is self-aldol, where the nucleophile and electrophile are the same molecules. The second type is going to be mixed aldol, where the nucleophile and electrophile are different molecules. And then the third type is going to be intramolecular aldol, right? Where the nucleophile is going to be the same molecule as the electrophile, like within the same molecule, like one molecule attacks itself, forming a ring. And I'm going to show you that example later. But for now, I want to go more into the mixed aldol, right? This is one example of mixed aldol where it's very clean, because this molecule here cannot be the nucleophile at all, right? Because if you look at this alpha carbon right here, this alpha carbon has no alpha protons, no hydrogens for us to deprotonate to make the nucleophile. But this nucleophile here does have a proton for us to deprotonate to become the nucleophile right here. So it's going to be clean. But for some mixed aldols, condensations like this, for example, where we have two different molecules that can both be the nucleophile and electrophile, right? For example, let's say this could be the nucleophile, this could be the electrophile, or this could be the nucleophile, this could be the electrophile. We're going to get 4 different products, right? And I'm going to show you those 4 different products right here. Let's say that we do a self-aldol with this red molecule here, right? And let's do the same trick. Draw out the starred molecule as is, copy and paste that, make a new bond between the star and dot, right? This right here is the new bond. The red dot is this red dot right here. And this red dot right here is attached to, be careful here, this star is part of that ethyl group, right? So let's draw that ethyl group coming out like that. And then this carbonyl or carbon double bond oxygen becomes an OH. The hydrogen here is invisible. And in this case, because we can get rid of the OH and put a double bond between the star and dot without breaking any octet rule, this is going to be the product for the self-aldol with this red molecule here, right? Let's do the same for the blue molecule. Draw out the blue star, make a new bond between the blue star and blue dot to do the self-aldol with the blue molecule, right? That's the new bond right there. This blue dot here is attached to a methyl group, which is that methyl group right there. And then OH coming from this carbonyl, which we can get rid of and put a double bond between the star and dot like that, okay? Now, this is going to be the mixed aldol. Let's say that we have used the red star and the blue dot, right? So let's do that. So red star right here, and then new bond to the blue dot, right? And this blue dot here is attached to a methyl group, which is going to be this methyl group right here. And then the carbonyl becomes an OH, which can get eliminated or dehydrated to create that alpha beta unsaturated carbonyl there. Now let's use a blue star reacting with the red dot, right? So copy and paste that blue star out. And then new bond to the red dot. The red dot here is attached to an ethyl group, so let's draw that ethyl group out like this. And then create a double bond right there, right? There was an OH there, but then we know that that can get eliminated to become a double bond, to make a double bond between the alpha and beta carbon right there, right? Now, most likely this will not show up on an exam, but this is just a good thought experiment to practice on how to predict the product quickly on aldol condensation reactions without doing the whole mechanism, right? But these are our 4 different products here. This might show up for Liebman's vocab, like how many different unique products can be formed from these like 2 reactants here with this reagent here, right? Okay, so that is mixed aldol. We could also like do retrosynthesis, like given any like alpha beta unsaturated carbonyl, you can cut it up to go backwards to figure out your reactants. Now, let's go over intramolecular aldol condensation. Okay, so this intramolecular aldol condensation is very important, especially for Robinson annulation, which we will go over after micro addition. Okay, so let's say we have oh yeah, another thing that I wanted to mention before that is that notice how the electrophiles that we've been working with have been aldehydes, right? And that's because if you compare like the carbonyl electrophilicity of an aldehyde versus a ketone, the aldehyde carbonyl is more electrophilic than the ketone, right? This carbonyl, an aldehyde, has a bigger positive charge because both carbonyls, right, of the aldehyde and ketone are attached to the oxygen, double bonded to the oxygen. But if you think about this aldehyde here, it only has 1 R group donating electrons to the carbonyl, which reduces the positive charge, right? But this hydrogen here is not an EDG, electron donating group, so it won't reduce the positive charge, right? But if you look at the ketone over here, the ketone has 2 R groups donating electrons to the carbonyl carbon, reducing the positive charge or stabilizing it even more, making it a weaker electrophile, right? So that's why an aldehyde is going to be a stronger electrophile than a ketone. And in intermolecular aldol condensations, right, where the nucleophile is separate than the electrophile is going to be the aldehyde, right? Since the aldehyde has a bigger positive charge. But for intramolecular aldol condensation, the electrophile can be the ketone because intramolecular reactions are very favored since they increase entropy, right? So ketones here can be the electrophile for intramolecular aldol condensations, right? So let me write that down. Can be the electrophile for intramolecular Aldol condensation reactions, right? And then these ones here are going to be electrophiles for both inter and intramolecular, intermolecular and intramolecular reactions. Okay, so let's give an example of that. So let's say we have, say this, right? This is very symmetrical, so this is going to be an easy example, but after this, I'll give you guys a harder example with a base. Okay, we have 2 carbonyls here, and we have 4 alpha carbons, 1, 2, 3, 4. Let's just say that this right here is the electrophile, right? This is the red dot right here. This cannot be the nucleophile, and this cannot be the nucleophile, because if it attacks itself, it's going to try to create a 2-membered ring, right? And that's impossible. We can't create a 2-membered ring. Now we're going to choose between this alpha carbon and this alpha carbon. If we choose this alpha carbon here and it attacks this electrophile, that's going to make a 4-membered ring, right? And that 4-membered ring is unstable because of a lot of ring strain and torsional strain, right? Now, if we choose this alpha carbon here, that's going to create a 6-membered ring, which is stable, right? So that's why we're going to choose this alpha proton to deprotonate and generate our enolate ion here, right? And I'm just going to show you guys the whole mechanism for this intramolecular Aldol condensation. And then the next problem, I'm going to show you guys how to predict the product quickly without doing the whole mechanism. So when we deprotonate that to generate this enolate ion over here, we're going to get this alpha carbon as the nucleophile. Remember, this oxygen negative charge is not the nucleophile. Even though it has a full negative charge, it could do resonance with that alkene right here to give a negative charge on that alpha carbon, which is less stable, making it more reactive, more nucleophilic, right? Which is going to then attack this carbonyl carbon here, right? So because the nucleophile is on within the same molecule as the electrophile, this is an intramolecular reaction, creating a 1, 2, 3, 4, 5, 6-membered ring. So a tip that I have for you guys is to draw out that base template out. So we know we're making a 6-membered ring where every single atom in a 6-membered ring is carbon. So let's draw that base template out like that, where this is going to be 1, 2, 3, 4, 5, 6, where 1 is going to be the star atom, 6 is going to be the dot atom, and this is the new bond that we formed between them, 1 and 6, right? Now, everything else is copy and paste. 1 has nothing, 2 has the carbonyl, right? 3, 4, 5 has hydrogens, 3, 4, 5 has hydrogens. If there was like a methyl group on 4, draw that methyl group on 4 like that. If there was an isopropyl group on 3, draw the isopropyl group on 3 like that. Okay, and a 6, right, has a methyl group, which is this methyl group right here. And it used to have a double bond oxygen, but it got kicked off into a single bond O-. Okay, now this is going to be the same as the previous mechanism, where the O- is going to get protonated by the proton source we have, which is water in this case, right? And for Lebenslast, even if you don't have heat, assume that you're going to go through aldol dehydration, forming the alpha beta unsaturated carbonyl, right? So once we do that, we're going to get this aldol product right here. But because we have an alpha proton between the carbonyl and alcohol, we're going to generate the enolate ion again, right? And prepare to kick out the OH irreversibly. Okay. Okay. Now we're going to reform the carbonyl. We're going to shift the double bond over there and kick out that OH irreversibly to give us our alpha beta unsaturated carbonyl. Like that. Okay. Now I'm going to show you guys how to predict the product quickly here without doing this whole mechanism for this intramolecular aldol condensation within the same problem. And then after that, I'll give you guys a harder example and then have you guys try it out, and then I'll go over it after that. Okay. So for this example here, let's say that this is the electrophile And this right here is the nucleophile, because that's going to form a stable 6-membered ring. Okay, so what I like to do is draw that 6-membered ring out, and I also like to number it, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Where 1 is the star here, and then 6 is the dot here, right? And this right here is the new bond between 1 and 6. Now 2, the carbonyl stays the same, right? 6 has the methyl group, so that's going to be the methyl group right there. And then the carbonyl on 6 right here becomes an OH, right? But we know that if we can, without breaking the octet rule, we can eliminate that OH and put a double bond between the star and dot, right? Between the alpha and beta carbon, creating an alpha beta unsaturated carbonyl. Okay, so that's the quick way to predict the product for aldol condensation intramolecularly without drawing the whole mechanism. Now, let me give you guys a harder example to try. Right? To predict the product quickly, and also just practice the mechanism as well, because it might show up for the exam. But you also have to use an code for that, but it could be different. You know, like the molecules could be different. Okay, so okay. Okay, let's try this aldol condensation reaction, predict the product quickly, and also practice drawing the mechanism. But try that, and then I will go over how to predict the product quickly first. Okay, so let's see how we could work through this here. We see 2 carbonyls, right? Which could be the electrophile, right? So let's say that we choose this to be the electrophile. That means that this alpha carbon and this alpha carbon cannot be the nucleophile, right? This alpha carbon here cannot be the nucleophile at all, because there's no protons coming out, right? There's no hydrogen there. So we cannot deproteinate that alpha carbon to make the nucleophile. That means that if we make this the nucleophile, that would create a 1, 2, 3 membered ring. That's extremely unstable. So I'm gonna get rid of that as the option for the electrophile and choose this as the electrophile, where this cannot be the nucleophile. And this right here, or this right here, could be the nucleophile. If we choose this, that would create a 1, 2, 3 membered ring, which is unstable. We don't want that. If we choose this nucleophile, that would create a 1, 2, 3, 4, 5 membered ring, which is relatively stable. So I'm going to choose this right here as the nucleophile. And I'm going to number it 1, 2, 3, 4, 5 to draw out as a template, right? And number it 1, 2, 3, 4, 5, where 1 is the star, 5 is the dot. This is the new bond between the 1 and 5. 2 has the carbonyl. 3 has the isopropyl. Right now, it's just copy and paste the decorations. 5 has this phenyl group attached to it. So let's draw that phenyl group out like this. Right, or you could just write pH for phenyl. And this carbonyl on 5 becomes a single bond OH, but we know that we can eliminate it to put a double bond between the 1 and 5, or the star and dot, to create an alpha beta unsaturated carbonyl for this aldol condensation product, right? Now, I would also practice drawing the mechanism, right? But to save time here, let's move on to retrosynthesis of intramolecular aldol condensation reaction, right? So let's say we have something like this, okay? And we are gonna try to break this up to figure out the reactant that created this in aldol condensation, right? So let's say we use this kind of base right here and this ethanol solvent right there, okay? So the first thing we do is very similar to how we did retrosynthesis for the regular aldol condensation, right? Or the self-aldol condensation or mixed aldol condensation. We're gonna focus on the alpha and beta carbons, which is this carbon and this carbon, right? That's gonna be unsaturated relative to this carbonyl here. Then you're gonna think that your alpha carbon is a star, beta carbon is the dot, make a cut between the alpha and beta carbon, and then copy and paste whatever is attached to the star molecule. Nothing changes to that, right? That's the nucleophile right there, right? And now, because this beta carbon here or the dot carbon here got like there's no bond here, right? We cut that off right there, right? This dot carbon here will have a carbonyl right there, right? A carbon double bond oxygen, because that is the electrophile for this intramolecular aldol condensation. It has an invisible hydrogen, which I'm going to draw out because this is an aldehyde right there. And this right here, you could leave as your answer, right? But to make it more clean, you can like linearize it. You can make it more straight, right? But this right here is going to be the reactant that created this alpha beta unsaturated carbonyl, right? Cyclic alpha beta unsaturated carbonyl. And this right here is an intramolecular aldol condensation reaction. Okay. Okay. So now let's move on to micro addition, right? So for micro addition, we're gonna do well, before we do micro addition, I want to go over this concept with you guys here. Let's talk about 1,2 versus 1,4 additions, right? So if you look at this structure right here, which is an alpha beta unsaturated carbonyl, right? This is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. We have two electrophiles here, right? The first electrophile is going to be this carbonyl carbon right here. And the second electrophile, this is kind of sneaky, is this beta carbon right here. And I'll show you why through this resonance structure. We could shift that double bond to create the bond here, popping this double bond out to the oxygen to give us this resonance structure right here, right? And we see that there is a full positive charge on the beta carbon, which is why this beta carbon and this carbonyl carbon is the electrophile. So for all alpha beta unsaturated carbonyls, think that that is an electrophile at the carbonyl carbon position and the beta carbon, right? The alpha carbon is not going to be the electrophile at all, right? So this alpha carbon here is not going to be the electrophile at all, okay? Now, depending on what nucleophile you have, either a reversible nucleophile or an irreversible nucleophile, that's going to attack either the carbonyl carbon or the beta carbon, right? So let's talk about irreversible nucleophiles because that's the easier list to remember, right? Because there's a few of them. There's going to be LDA, or you might see that in this form, right? There's going to be N-butyllithium, right? Which is going to be like that, right? There's going to be NaH, right? Which is a hydride ion. What else is there? Let's see, LDA, N-butyllithium, Grignard reagents, right? Organometallic reagents, right? RMGBr, or organolithiums, RLI, right? Where the R minus is the nucleophile, right? NaH is the hydride ion. These irreversible nucleophiles will attack and stay on the carbonyl carbon as the electrophile, right? So for example, let me just give you an organometallic example right here. Let's say we have this alpha beta unsaturated carbonyl, and we react this with this Grignard reagent and second step acid workup. right? So this green reagent here, the atom directly attached to the magnesium is going to be the nucleophile because it's negatively charged. It's going to attack that carbon-carbon, push the bond onto the oxygen. And I'm going to leave the hydrogen out here as invisible, right? This is the dot carbon. This is the star carbon. This right here is the new bond formed between the star and dot carbon. This star carbon here is attached to another carbon, which is this carbon right here. The MGBr dissolves away into the solution. And then the second step, acid workup, comes in to neutralize and protonate the O- to become an alcohol, like this. Okay, so that is going to be the irreversible reaction, where it stays on the carbonyl-carbon. But now, if we think about reversible nucleophiles, which the most common one that you're going to see in this unit is going to be the enolate ion, right? The enolate ion, right? Which is going to be the same nucleophile as what we did for aldol condensation. So it's going to be like either in this form, right? Which is the same thing as this form right here. They're just resonance structures of each other, but the nucleophile here is this alpha carbon right there, right? There's also going to be like the regular nucleophiles you're used to seeing, like NaOH, NaCN, NaN3, right? You can also see enamines as well, right? Where the alpha carbon here is the nucleophile, right? But let me show you the mechanism for that and how to predict the product quickly. So let's say we have this alpha beta unsaturated carbonyl, and then we react this with first step is going to be this enolate ion, right? And then the second step is going to be acid worked up. Okay, so the O- is not the nucleophile because we know that from resonance, this alpha carbon here is going to be negatively charged, which is more reactive. So we're going to reform the carbonyl, have the alpha carbon first attack the carbonyl carbon because that is like still more electrophilic than this beta carbon, right? And that's very important for vocab, but it will not stay there, right? Because this is reversible. In the previous example, conceptually, this is irreversible because we're using strong, very reactive nucleophiles that once we do the reaction, right, we cannot kick out this group again, right? Because if we kick it out, it's going to be kicked out as R-, or if we use hydride, H-, which is very unstable. It does not want to happen like that, right? But for the reversible ones, it is stable because of resonance, right? Or some other factor making it more stable. So that's just conceptually, but let's just continue with the mechanism here, where this is the dot. This is going to be the new bond between the star and dot. Star is attached to this group, which is that group right there. And then from here, we're actually going to reform the carbonyl and kick out this group right here. So in this case, I'm just going to give a negative charge on that alpha carbon, right? You can like create double bond here and then push it, the double bond onto the oxygen. But for this case, I'm just going to draw out the enolate in this form. And then from here, we're going to attack the less electrophilic beta carbon and form a double bond there and kick out push the double bond to the oxygen right there to give us this intermediate right here. And the reason why we do that is because this is going to lead us to our thermodynamic product, right? The more stable product, the more stable alkene. In the previous example with the irreversible nucleophile, we formed the kinetic product, the less stable alkene, right? And that's because we used an irreversible nucleophile, right? And a very unstable reactive nucleophile. But in this case, since we're using a more stable reversible nucleophile, we have time, energy to get to the more stable alkene, right? Which is going to create this di-substituted alkene right here. So I'm just going to draw that out like that, where this is the dot. This is going to be the new bond between the dot and star, right? And this star here is attached to this carbonyl. And then from here, this right here is going to get protonated by the second step, but the O- is not going to get protonated. This alpha carbon is, right? So we're going to reform the carbonyl, have the alpha carbon grab the proton from the acid and form this product right here, right? So this alpha carbon here will either be the nucleophile or the base, right? In this case, it's acting as a base because it's getting protonated by the acid, right? And what we did here was basically microaddition, right? Because microaddition, the nucleophile is going to be the enolate ion, the electrophile is going to be the alpha beta unsaturated carbonyl, specifically the beta carbon, right? This carbon right here. And the product is going to be a 1,5 dicarbonyl. 1,5 dicarbonyl, like that, right? Because if you count the distance between the two carbonyls, that's a 1,5 dicarbonyl right there. Okay, now let me create a chart for you that would summarize what we just did, right? Because this could get jumbled up very easily. Like the end of 118B is like very stressful. I remember taking it and it's like very fast paced as well, even like the regular quarter, but you guys are taking it in summer session, which is like extremely hard, but hopefully this will help. All right, so let's talk about aldol, and there's the 3 different types. Remember, there's self aldol, there's mixed aldol, and intramolecular aldol. And let's talk about micro, right? So the nucleophile for both aldol and micro is going to be an enolate ion, right? Where the enolate ion is going to be like this, where specifically it's going to be the alpha carbon right there, right? Because of resonance. When we draw the resonance, we see the negative charge on the carbon is less stable, making it more reactive, right? It's not going to be the oxygen minus ion, right? Oxygen minus, it's not going to be that. The electrophile for aldol is going to be the carbonyl carbon, right, of an aldehyde, right? Or remember when we went over intramolecular aldol condensation, a ketone if intramolecular. If it's an intramolecular aldol reaction, right? Okay. For Michael, it's going to be the beta carbon of the alpha beta unsaturated carbonyl. Okay. The product for aldol is going to be, if you cannot do aldol dehydration, it's going to be an aldol. But if you can do aldol dehydration, you're going to create the alpha beta unsaturated carbonyl. And then the product for Michael is going to be a 1,5 dicarbonyl. Okay, now I want to give you guys one more example for microaddition because I want to show you guys how to predict the product quickly for that. Let's say we have this alpha beta unsaturated carbonyl and we react it with, let's say, this enolate ion right here, right, with acid workup. Here's how to predict the product quickly. This alpha carbon here is the nucleophile. This is the carbonyl carbon. This is the alpha carbon. This is the beta carbon. Because this is a reversible nucleophile, our electrophile is going to be this beta carbon right here, right? So I'm first going to draw out the starred molecule, which I know when I reform the carbonyl, the starred carbon is going to attack the dot carbon. So that's why I drew a carbonyl right there. There's going to be a new bond between the star and dot. This dot here is attached to 2 methyl groups. So let's draw those 2 methyl groups out like that. And it's attached to 1, 2, 1, 2. And then that's where the carbonyl is, which is going to stay as a carbonyl, which this carbonyl is attached to the cyclopentyl group. And we could confirm this as the product by counting the distance between the 2 carbonyls, which is going to be 1, 2, 3, 4, 5, 6. So I did something wrong here, right? Because the product for micro addition should be a 1,5 dicarbonyl, but this right here, 1, 2, 3, 4, 5, 6, that's way too long of a distance. So let's see what we did wrong here. Reform a carbonyl. Okay, I see what I did wrong here. This is not an enolate ion because like this is an sp3 carbon right here. It cannot do resonance, right? So I drew out the nucleophile incorrectly. So this right here is going to be the nucleophile because now we can do resonance. Now we can reform the carbonyl and give a negative charge on that carbon right there. So let's redo this. Carbonyl, star right there. New bond between star and dot. Dot is attached to 2 methyl groups, 1, 2, and then this dot is attached to CH2 ring, and then cyclopentyl group coming out of it like this. Okay, now let's count the distance between the 2 carbonyls. 1, 2, 3, 4, 5. We have a 1,5 dicarbonyl, which is good for micro addition. Okay, now let's go over Robinson annulation. Now, Robinson annulation is a big boy reaction, right? Robinson annulation. It's going to combine a lot of the things we talked about today, where the first reaction is going to be a micro addition, and then the second reaction after that, following that, is going to be intramolecular Aldol condensation reaction. Okay, so, and that's because we're still in basic conditions, and once we end at this 1,5 dicarbonyl here, we're gonna, like, if the reagent is a base, this can do an intramolecular Aldol condensation, forming either 5 or 6 membered ring, more typically 6 membered ring. So let me give you an example of that. Okay. Now let's just do a comprehensive one right here, like this. Okay. So the first thing here, we have a ketone reacting with the first reagent with a base. So we're going to look for the most acidic proton, which is going to be one of these alpha protons here. It doesn't matter because it's symmetrical. If it was asymmetrical, you could get different products, right? But let's say that we form this enolate ion, right, which is a reversible nucleophile. And the nucleophile here is this alpha carbon. Then we bring in the second step of this alpha beta unsaturated carbonyl, where because this is a reversible nucleophile, the electrophile is not going to be this carbonyl carbon, but it's going to be this beta carbon right here. And then I'm just going to predict the product quickly here. You can practice the mechanism if you want, but to predict the product quickly here, I'm going to have the star molecule make a new bond with the dot molecule. That's the new bond right there. And that happens by reforming the carbonyl, having the star attack the dot, and then push the one to that, and push that the one to the oxygen, right? Which this dot carbon is attached to a methyl group, and then the CH2, and then that's going to be the carbonyl still, right? Okay, it was an O minus, but with the inlet here, but then it gets protonated, right? This alpha carbon gets protonated by the proton source we have, which is ethanol. Okay, now from here we have a 1, 2, 3, 4, 5, 1,5 dicarbonyl. Now we won't stop here because we're still in basic conditions, which we're going to do intramolecular Aldol condensation. We have 2 possible electrophiles, right? So I'm just going to erase the star and dot to make it more clear of what we're going to do here. This could be the electrophile, or this could be the electrophile. Let's see this as electrophile, right? If this is the electrophile, this alpha carbon and this alpha carbon cannot be the nucleophile. It's either going to be this or this. So that's going to create a 1, 2, 3, 4, not that. This is going to create a 1, 2, 3, 4, 5, 6. It could be that. Okay, now let's talk about this one right here, right? 1, 2, 3, 4. Nope. 1, 2, 3, 4, 5, 6. Yes. Okay. Now for the exam, right? We see that both of these carbonyls here can be the electrophile, right? If this is the electrophile, this is going to be the nucleophile. If this is the electrophile, this is going to be the nucleophile. But on the exam, they're going to write it in a way where you're only going to get one possible nucleophile, one possible electrophile, forming a stable ring, right? But when I created this problem here, I did not know that there's going to be two possible answers, right? So to prevent that, let's add a methyl group right here, right? Methyl group right there, methyl group right there. Now, if we see that this is the electrophile, this can no longer be the nucleophile because there's no alpha proton there to deprotonate and make the nucleophile, right? So that means that this cannot be the electrophile. This has to be the electrophile, and this right here has to be the nucleophile, creating a 1, 2, 3, 4, 5, 6-membered ring, right? So let's draw that 6-membered ring out, base template for intramolecular aldol condensation. 1, 2, 3, 4, 5, 6, where 1 is the star, 6 is the dot. This is the new bond between the 1 and 6. 1 has a methyl group attached to it, which is this methyl group. 2 has a carbonyl. 3 has a methyl. 4 has a methyl. 5 has hydrogens. 6 has a tert-butyl, right? And it also has a carbonyl, but we see that that carbonyl becomes an OH, which we can eliminate and put a double bond between the star and dot without breaking any octet rule to form an alpha beta unsaturated carbonyl, right? And that's going to be the product for Robinson annulation. And now let's end off this video by doing retrosynthesis of Robinson annulation, right? Which could show up for a synthesis problem, right? So let's say we have this as the product, right? And we want to break it up to find out the reactant for this Robinson annulation. So find the alpha and beta carbon relative to the carbonyl that has an unsaturation between them. Cut that. The alpha carbon is the star, beta carbon is the dot. And then if we go backwards here, let's copy and paste everything like that. This is the star. Okay. And then this is the dot, which this dot has a carbonyl, right? This is the thing that it came from. Now, this is a 1, 2, 3, 4, 5. We can cut this even more by finding the alpha beta unsaturated carbonyl, right? So once we have gotten our intramolecular aldol condensation reactant, now we can cut this even more to find the microaddition reactants, right? Now let's say if this is the star right here, this has to be the beta carbon, right? If this was the star right here, this has to be the beta carbon. So there's actually multiple different reactants that we can create from here, right? This could be the star, this could be the dot, creating these as the reactants for microaddition, right? Okay, where this is the star, and then the dot is going to be the beta carbon of this alpha beta unsaturated carbonyl, right? Now, if we chose this as a star and then this as the dot, right, that's going to create this as the reactants for microaddition. Right? But on her exam, she might form a question that you only get one possible set of reactants instead of two possible set of reactants like that. But maybe not, right? Maybe there's two possible ones, and if you write this for synthesis, you get full credit, right? And then you might see this, or this as the starting material for the synthesis, and this as the ending material for the synthesis. And this is how you would go backwards retrosynthetically to figure it out and do synthesis, right? And the reagents here would be base, right? It could be NaOH or ethoxide or alkoxide ion, right? Second step, acid workup, same as for this. It could be ethoxide. Second step, acid workup. And same as for here as well, right? Basic conditions, okay? And I hope that helps. That was just a part of chapter 18, which is like a very big part of chapter 18. But I wanted to make this video for you guys to help you guys prepare for the final, because I know you guys have a little time to learn it and absorb it and practice. But I will have two 2-hour final review sessions for Levin's Chem 119B, the summer session, right? Part 1 is going to be on Tuesday, September 9th from 9 to 11 p.m. Part 2 is going to be on Wednesday, right? September 10th, 9 to 11 p.m. And the location can be found in the description. And feel free to DM me on Discord or Instagram any problems or questions you have, so I could prepare and create problems for that. And I hope that helps.